Hi, it's Bruce again in my Colorado Rocky Mountain lab. And what I got to show you right now is a B&K Precision 30 megahertz oscilloscope, model 1474. It's a pretty straightforward scope. 30 megahertz bandwidth, dual trace, AC, DC, ground, does dual trace at the same time or independent traces, and then it has an additive feature where it adds the two traces together. Also has a channel B polarity switch, so you can wind up actually subtracting as well. There's a horizontal variable sweep time control with 20 ranges. Covers from 0.5 seconds per division up to 0.2 microseconds per division. And automatic triggering, you can trigger on A or B channels. You can use AC or DC coupling. You've got low frequency and high frequency filters. You can choose an external source or an AM detector for your source of triggering. And got an external port for the triggering right here. We've got the 1 kilohertz 0.5 volt peak-to-peak calibration outlet there. A-stick controls. You can adjust the trace horizontal, I guess you call that trace rotation. That's adjustments in the back. Basically that describes it. The unit is in really nice condition. Beautiful paint. Few if any scratches. Well, actually I know there's a nick or two on the bottom of the unit. See if we can get a look at this. Even the bottom of the unit looks great. A little ding on the side and about the middle there, and there's a scratch on the bottom left down there. I don't know if you can see it on the screen, but you can take my word for it. And then the back. Currently, we are looking at a 10 kilohertz signal, and right there, that's 10 microseconds per division times 10 divisions. So you got one cycle in 100 microseconds, which would be 10 kiloseconds, or 10 kilohertz. And if we were to change the frequency to 20 kilohertz, 30, 40, 50, you can see the traces multiplying. All right, well, we've opened up this B&K 1474. I just wanted to give you a look on the inside and show you that it's been cleaned up and looks pretty decent. Nice and neat layout. Everything's clean. And we're going to button it up and take it through a few tests, and we'll get back. Okay, well, I can imagine there's guys out there going to tell you, why would you want to look at a 30 megahertz scope? Oh my goodness, you need at least 100. And I'll tell you, a lot of it's got to do with what you're doing and what your needs are. If you're a fledgling newbie and you just want to dabble in this to see what it's like, then you don't necessarily need to spend big bucks. Secondly, if you're not going to be working in radio frequencies up, then again, maybe you don't need to invest the big bucks. 30 megahertz is a pretty good range. I mean, that covers audio, that covers ultrasonics, that goes up into Low range radio, AM covers section of shortwave. So you're already covering a good portion of the spectrum. And most of the time, I find myself working in frequencies 10 megahertz and below anyway. I look at the standards on my bench. I'm looking for noise on my power output systems. I'm looking for what's happening on my audio coming out of the circuits. Trying to track down noise in any kind of a circuit. So I don't need 300 megahertz or 100 megahertz to be able to do that. So anyway, it's a very good scope. It's got a lot of great characteristics. Nice bright display. We can turn the intensity up. We can turn the intensity down. Have control of it. Focus out. Back in again. We've got illumination for the gradical. Notice the checks are now lit, and then I can take it back out. And right now we're looking at a 500 kilohertz signal. There would be our highest range right there. We are on 0.2 microseconds per division. We're covering 10 divisions in one cycle. So 0.2 times 10 would be 2 microseconds. So 1 over 2 microseconds would be 500 kilohertz. So there we are. We just backed into it. And it's correct. Let's take a look at some other frequencies. We'll take a look at 1 megahertz here. Okay. There's 1 megahertz. If we go to 1 microsecond per division, then we should see in one division we complete one trace, and we do. So there's 10 of them across there. We are right now feeding in 0.6 volts total. And we are on 0.1 volts per division. So we go up 3, we go down 3. That's 0.6 total. We're doing it on both the left and right channel, both channel 1 and 2. Or A and B, or however you want to call it. This is A and B on this particular machine. So our amplitude is correct as well. Let's take that amplitude down to 0.3. Should see ourselves going up 1.5, down 1.5, and we do. There's 0.2. We go up 1, down 1. All right, let's change our frequency again. We'll go to 10 megahertz. We're doing 10 megahertz. We're doing both channels simultaneously. And we will go that's 0.4 volts, so we should be going up and down 2. We've got a little bit of signal loss, but that would be about right because we expect it to fall 3 dB at 30, so we're climbing. We're at 10. We're 1/3 of the way there. We should come down a little. Let's take ourselves to 100 kilohertz. Okay. One cycle in 10 divisions. We're at 1 microsecond per division. That's 10 microseconds. That'd be 100 kilohertz. So there you go. Let's take that down to 0, and we'll go to 10 kilohertz. All right, we now see one cycle crossing in 10 divisions. We are on 10 microseconds per division. And 10 microseconds times 10 would be 100 microseconds. That would be 0.1 second, which would be 10 kilohertz. That'd be 10, yeah, If it was 1 second, it'd be 1,000 hertz. It's 10 kilohertz. So let's take ourselves to 1 kilohertz. All right, we've gone to 1 kilohertz, and we are at 0.8 volts. We right now see in 10 divisions at 0.1 milliseconds per division. That'd be 1 millisecond, so that's 1,000 hertz. And we are on 0.2 volts per division on both the A and B channels. We're reading both simultaneously. We see 0.2, 0.4, up and down, that's 0.8, and that's where we're at. Okay, let's take our frequency down even more. Do 100 hertz. Okay, we are at 1 millisecond per division. We got 10 divisions for a sweep. That's 10 milliseconds. And 10 milliseconds would be 100 hertz. And again, we are up 2 divisions at 0.2 volts per division. So we're at 0.8 volts. Up. Yeah, we want to go down again. All right, we're on right now a 10 hertz. And once again, 10 divisions, we see 1 trace. We're at 10 milliseconds per division. That's 100 milliseconds for 1 trace. If we were at 1 second, that'd be 1 hertz. We are at 0.1 seconds, so that'd be 10 times more. So this is 10 hertz. And we're up 2 divisions, down 2 divisions, times 0.2 volts per division. That'd be 8.8 volts. Okay. We're going to take her down to 1 hertz. This will be difficult to read, and we're going to go DC in order that we get full trace. Okay, basically we're seeing 1 trace. Now 1 trace is in 0.1 seconds. And 0.1 seconds in 10 divisions would be 1 second, so we're at 1 hertz. And we are up 2, down 2, so that's a total of 4 divisions times 0.2 volts per division. That's 0.8 volts. So there we are. We've gone from 1 to 10 megahertz there easily. All right, we're going to go ahead and take her up to 30, but we can't do that with both channels fed at the same time. They compete with each other, and their impedance at that frequency is a little different. So we're gonna just feed one at a time. We're gonna put 1 kilohertz in here to begin with. All right, we're at 1 kilohertz, and we're gonna feed enough voltage in here to drive ourselves up and down 4 divisions. That looks like it right there. So that's 1,000 hertz. We've got 1.6 volts going in here. Just double check that. 1, 2, 3, 4. 8 divisions times 0.2 would be 1.6 volts, which would be right. So we're at 1.6 volts. We've gone up 4 divisions and down 4 divisions. Now, when you're checking 3 dB, the 3 dB point, if the 3 dB point is going to be at the point that you fall to 2.83 divisions on this screen now. You started at 4. If you hit 2.83, you've decreased 3 dB. Let's go ahead and we'll increase our frequency. There's 10, 20, 30. So right now, we've fallen one division from the top. So we were at 4 divisions, we are now at 3. If we were at 2.83, that would be the 3 dB point. So we've actually beaten the 3 dB point slightly. And make it more visible, we'll increase it by a factor of 10. The overhead light's not helping a whole lot here at this speed. But we do have, we've exceeded the 3 dB point of 2.83 divisions. We're at 3 divisions, so there we go. Okay, here we are at 30 megahertz on channel B, and we are going up and down about 2.9 divisions. So 2.83 would be the 3 dB point. We're at or exceeding it. So there we are, channel A and B both at 30 megahertz. We've got our bandwidth. That's really what we wanted to know. And I'll tell you, you're going to spend most of your time 10 megahertz and below anyway. And that would be looking at this. And we are back almost at maximum four divisions up and down now. So I demonstrated while we were working here, I pulled out the position control. That gives me 5 times of gain in the horizontal, and you can see we've expanded the horizontal to where it's easily seen. Here we're at 10 megahertz at a much slower speed on the horizontal, 1/5 of the speed actually. All right, here we're looking at the trace. This is a 1 megahertz trace. All right, 1 megahertz. We've got 2 cycles. We're on 0.2 microseconds per division. And what I wanted to demonstrate is if I hit the channel B polarity button here, that channel is going to invert itself, and you're going to see 2 sine waves out of phase. And forms that kind of an interesting pattern. And if I put this thing on additive, basically those 2 waveforms, one positive, one negative, when added together comes out to 0. If I uninvert, then we get double the waveform in amplitude. It added it that way. So the add and the invert are working fine as well. So all in all, it's a nice little unit. It's working great. It's going to be a nice starter unit for somebody, or it could be a permanent unit for somebody who's working in audio through low signal radio, low wave. Let me get the light back on. I'll tell you what else we got going. Okay, well, the 1474 also has an XY position on the time base. They don't call it XY, but they have instead, at the very limit of sweep, they've got channel B. And what they're doing is they're using channel B as the horizontal time base. So whatever goes in on the signal on B, that's what's establishing the sweep across the screen. And then you put in your signal on channel A, and you are comparing A to the sweep of B. And right now, what I'm doing is I'm trying to produce a Lissajous pattern, and I want to see something that looks like an ellipse or a circle, because that will mean that my 2 incoming signals are of the same frequency. And I know that the chances of my Ray Caldana 20 megahertz sweep generator up there being exactly on frequency, pretty slim. It's not designed for that. However, this unit right now is carefully calibrated to 10 kilohertz, as close as I can get it on the dial. So I've got 10 kilohertz plus or minus running my horizontal sweep, and then I'm using this DDS signal generator to generate my my channel 1 or input A, which gives me the vertical. What I'm going to do is I'm going to change the frequency on this DDS, which is very precise, and I'm going to try and stop that wave from moving. When I do, I'll know the frequency of my Ray Caldana up there. So let's go ahead. Right now, I know that I'm supposed to be around 10,000, so this is 9,995. All right, let's go to 6, 7, 98, 99. There's 10,000. That's 10 kilohertz. 10,001, 2, 3, 4. You can see it's slowing down. 5, 6, 7, 8, 9, 10, 11. Very close. In fact, that's it. So right now, that Ray Caldana is 11 hertz over 10 kilohertz. And you'll see that it's going to drift over time. Which direction at the moment, I'm not sure. Probably upwards as it's heating up. Let's try 12 now. Yep, it went up a hertz. Now, this Lissajous system using the XY or A versus B, whatever you want to call it, is a fantastic way of calibrating one signal against another. Let's say that on channel B, where I have my Ray Caldana right now, I was feeding in a signal from a very precise oven-controlled oscillator. And that oscillator, it's going to be my bench, or is my bench oscillator, and it gives me a 10 megahertz signal that is, for all intents and purposes, spot on. But now I have a piece of equipment that has an internal 10 megahertz oscillator, and I want to adjust the internal oscillator on it so it's as close as possible to my bench oscillator, my master. Well, I would put that internal oscillator on that piece of equipment. I'd feed the signal in here, and then I would adjust my incoming signal on this channel until I matched my horizontal. And when I got that signal here to stand still, I'll know that the two are matched together. It's far more accurate than any frequency counter because you don't have to wait for the counter to give you the results. And it will give you a fraction of a hertz difference. You'll see it show up on the screen. Fantastic way to do that. And it's one of the uses of the XY that's worth having. I mean, there are others. I think I've seen people comparing charged versus current on capacitors and things like that. But let's see, we probably drifted up now another degree or two, or another hertz or two. No, we went down. Here's 12 going to 11, going to 10, going to 9, going to 8, 7, 6, 5. So 6 is it. So the XY is working on this scope beautifully. Okay, along with the unit will be a user manual, a service manual with the calibration methods. This unit is fairly easy to calibrate. You just follow the directions in the manual, and takes very little special equipment, really almost none at all. If you have a generator that can generate a signal, and if you don't, you use the 1 kilohertz 0.5 volt signal out of this thing, and you can calibrate with that. But most of it is observation and aligning traces. So I'm going to wish you happy bidding, and we'll see you next time.